start from current slide. But before we do, I'll go over these two announcements again. College transfer day is coming up 1 week from yesterday, next Wednesday, February 12th, 9:30 to 11:30, Birmingham West Campus, Academic Building, B Hall. All up and down the hall, they'll have tables for all these schools, as many of them show up. Then on Thursday, 1 week from today, next Thursday, they'll be here on this campus, 9:30 to 11:30. That's February 13th. And that'll be in this building near the cafeteria. It may be in the cafeteria, but I'm thinking it's going to be next door at the faculty staff dining room or in the hallway nearby or somewhere like that. They may have a few in the cafeteria themselves, but it just seems like there's not going to be room for that many people there. Not with the end of breakfast, the beginning of lunch happening. And then the great REU is one of several, but this is the only one I have printed off. 10-week internship. They don't say exactly when the beginning and end dates are, but they're just about like our summer terms because they're their summer terms. Deadline appears to be February 17th. I was just seeing if they could list anything about the dates. They may be in here, I just haven't laid my eyes on them. But it's a great program, fantastic program. Now, one other thing, and this won't affect you because you're all covered. I think Josh is all covered, so it's not an issue for y'all. But you may run into someone it's an issue for in one of your other classes or friends or whatever. The end of every day, I put all the attendance in the computer, okay? Monday evening, I did it, no sweat, just the same as always. Tuesday, when I went to do it, at the end of the day on Tuesday, when I went to do my first class, it indicated I hadn't done the attendance all term, and I had done it every day. So I went back to the first of the term, clicked on that, and one person who had been there, and I had put his attendance in, now all of his attendance was blank. So I had to go in every day to put his attendance back in. I thought I knew probably what had happened, but I wasn't sure until I got to the last day, which last Tuesday, when I was putting that attendance in, I saw that there were also 2 people who weren't listed that had been listed. I said, okay, what they've done is removed all unpaid students. And evidently they removed him either by mistake and put him back in, but of course that wiped out his attendance, or they took him out and then he paid and then they put him back in. Either one of those scenarios is a possibility. And then in my other classes, I kept running into either people who that had happened to or people who had not, who were just missing from the roll. So if you hear anyone saying, I can't access blah, 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 you know, the student suite, Blackboard or something like that, they may have been removed from the class. So tell them gently, you might want to check on your cashier window or the records office or somewhere just to see if you're still enrolled, because that's probably the issue. Something else happened on Thursday. They wanted us to report all students who had not shown up all term. Paid students who had not ever attended the class, those are called no-shows. And once we report those, then they remove those from the roll too. So they removed non-paid students already, and then they're in the process of removing no-shows. So it doesn't affect you or Josh at all, but just to let you know in case anything happens. So in my differential equations class, the 2 people who had been coming up to before then had not paid, and the one person who had paid had never shown. So I thought, I'm going to lose my whole class. But when I went to do Wednesday's attendance, I saw those two guys who had both paid before they got thrown out. Now they'll probably throw out the other guy. I don't know. It's up to them and him or whatever. Okay. Any questions on anything we've done so far? All right. Now, where we got to last time was Chapter 2, Matrices, 2.1, Operations with Matrices, and we had just started talking about how to do multiply two matrices. Okay? And they have a big, hairy-looking thing at the top of page 44, and that's where we're beginning today. So here are the matrices that we have. Probably not big enough, but I'll try. A11, A12, A13, dot, 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 up to A1, and this subscript is N. Okay? A21, A22, A23, dot, 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 up to A2 sub N. A31, A32, A33, dot, 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 up to A sub 3 N. Dot, 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 down to A sub M1, dot, 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 down to A sub M2, dot, 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 down to A sub M3, and dot, 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 everywhere, dot, dot, okay, to A sub M N. Okay, so there's our first matrix, matrix A, and it happens to be M rows, N columns, so that's an M by N matrix, right? Okay, we're multiplying that by matrix B, and that'll be B sub 1, 1, B sub 1, 2, B sub 1, 3, dot, 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 to B sub 1, they use P here, okay, and B sub 2, 1, B sub 2, 2, B sub 2, 3, dot, 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 to B sub 2P, and B sub 3, 1, B sub 3, 2, B sub 3, 3, dot, 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 to B sub 3P, okay, dot, 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 down to B sub N1, dot, 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 down to B sub N2, dot, 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 down to B sub N3, and dot, 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 to B sub NP. Okay, that's an NP. So here's your matrix B that you're multiplying by a matrix A, and B is an N row P column, N by P. Now, obviously those are not necessarily the same size. They could be if they're square matrices, like an M by M, you can multiply by M by M, no problem there. But if they're rectangular matrices, they're definitely not going to be the same size. Okay, adding two matrices, they got to be the same size. Equality of matrices, they got to be the same size. Subtracting two matrices, they got to be the same size. Multiplying two matrices, unless they're both square of the same size, they've got to be different sizes. If they're rectangular, they're going to be different sizes. Okay? Now, what is the result of this? This is a matrix we're going to call C, and C is going to be C11, C, yeah, I can't write. C12, C13, dot, 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 up to C1P. Okay? Yeah. And we'll have a I can't write, C21, C22, C23, to C2P. And a C31, C32, C33, to C3P. Okay, down here to CM1, down to CM2, down to CM3, and then to CMP. So the dot product, or the product of these two matrices, is going to be another matrix, C, and its dimensions have to be. Now here's the requirement. These two matrices, they're different sizes, but one thing that has to be true, the number of columns of this must be the number of rows to that. Has to be. If you're not going to be able to multiply. So you basically wipe those two out, and that gives you matrix C to be of dimensions M by P. So it's not necessarily going to be the same size as either one of those. It could be. If this was M by N, this is an N by N, that would be okay. And then that winds up being an M by N too. Yeah, it can be the same size as this. Or an M by M, an M by P, that would be an M by P. So yeah, it can be the same size, but it's, unless they're all square matrices of the same size, they're not all three going to be the same size, ever. Unless they're square matrices of the same size. And that's going to be the requirement. Now, how do you get the C33 entry here? You get it from the third row of A and the third column of B and the products of those. These. Yeah. That's how you get any one of these here. And when we do some, I don't know if you had a chance to watch the video, but I showed you how I usually line it up and the questions I ask myself and how I get it to happen. They do sort of the same thing, maybe not quite as systematic or something as I do, but the way I do it just seems to help me some. Okay? Now, so I just picked the C33, maybe not a good choice. Let's just pick the CIJ entry. It might be one of these down in here somewhere, that is a ... Okay? How do you get that CIJ entry? Well, it's the AI1 times B1J. Notice the inner ones have to be the same, and the outer ones have to be the same as that. Plus AI2 B2J plus AI3 B3J plus ... up to your AIN BNJ. You add all those together, yeah, and that gives you your CIJ. So whichever your ith row of A times your jth column of B, those corresponding entries you multiply and add and keep the sum going. Okay. I don't find that particularly enlightening, okay, but they put it in here, so I tried to reproduce it. Okay, so let's clear this out of the way. They have a little discovery here, so let's just see what this discovery tells us. Two very simple 2x2 matrices. A is 1, 2, 3, 4. Very creative matrix. 1, 2, 3, and 4. B is 0, 1, 1, 2. Okay. It says find A plus B and B plus A. That's not going to be too hard. A plus B. Can we do that just right off the top? First, can you add those two? Yeah, they're the same size. So what do you get? 1, 3, 4, 6. Okay. Let's do B plus A. Can you do that? Okay, what does that give you? 1, 3, 4, 6. Yeah, it doesn't matter. Adding two matrices, as long as you can add them, that's a commutative process. It doesn't really matter. Okay? So is matrix addition commutative? Yes. Commutative. Matrix addition is commutative. Okay, it's commutative. All right, let's do A times B. Can you do that? Yes, you can, because this is what size? 2 by 2. This is what size? 2 by 2. And because those inner two are the same, you can eliminate them, and your result is going to be a 2 by 2. Okay? So, here's how I do it. I put blanks in for those 2 rows and 2 columns. Okay? Now, what entry would this be? Subscript. What would it be? 1, 1, right? This is the 1, 1 entry, right? So what you do, you take the first row of A by the first column of B, and that's what you multiply. What does that give you? 0. So, 0 plus 2 is 2. Okay? All right. Then what entry is this one? No. 1, 2. Yeah, 1, 2 entry. So you take the first row of A by the second column. Okay? And that is plus is 5. Okay, so that's 5. That's how I do it. Decide my size, okay, from looking at the 2 matrices there, put them in place, then identify the element, and then use the first subscript as the row of the first one, second subscript as the column of the second. So what would be this subscript? 2, 1. So you take the second row here, first column here. What's that? 4. Okay, I'm tired of sitting. My knee hurts every time I get up, so I'm going to lean over and do it. And then this one, of course, is the 2, 2 entry. So second row by second column, which is 3, 6, 9. 8. 8, okay. And that gives you 11. Okay. Well, that reminds me of a dumb thing I've seen. People making fun of the Scottish accent. It was a really cute little video of someone walking into the elevator that you don't press a button, you tell it what floor you want to go to, so it's voice activated. And the Scottish guy says, 11, or however they pronounce it. And the voice comes on and says, I'm sorry, would you please repeat that? And he said, 11, or however he said, and it just keeps going, and finally said, get off the elevator. Because I couldn't figure out where he was saying. But anyway, 11, okay. So let's do BA, okay? Now, frankly, to do this, can you do that? I'm going to move A over here. just because it's a bit easier. Okay. Can you multiply that? Yeah, because A is a 2 by 2. And this time it's the inner 2's that are gone. Same 2, okay. And this gives you a 2 by 2 again. And there are your 4 blanks. And this time we do it this way. Okay. This is the 1, 1 entry, so that'll be is 3. Try to do it without sitting. Okay. This is the 1, 2. So it's first row by second column. 0, 4. Well, goodness gracious, this thing won't write. Okay. And this entry is in 2, 1. So it's second row by first column. 7, okay. And then the 2, 2, second row, second column. Is 10. Okay. Now, the question being, is matrix multiplication commutative? No, nowhere close, okay? Not at all similar, okay? So don't ever imagine that it could be. So, no matrix multiplication not commutative, except in some very special cases, and it will be, okay? We'll hit those later. If they are commutative, you got some special matrices on hand. All right, let's do example 5, okay? And this one you can see LarsonLinearAlgebra.com for an interactive version of this type of example. The old edition didn't have those. They added this in this newer edition. So here is the A, okay? 1, 0, 3, 2, negative 1, negative 2, matrix multiplied by negative 2, 4, 2, 1, 0, 0, negative 1, 1, negative 1. Okay. Before I even begin, especially before I begin, I want to see if this will even multiply. What size is this one? 2 by 3. What size is this one? 3 by 3. Will they multiply? Yes, because the inners are the same, so mark them off. And the product matrix will be what size? 2 by 3. So since I know that, I'm going to put 2 rows, 3 columns. Okay? First entry here is what? Index? 1, 1. So we'll do first row here, first column there. That adds to negative 5. Excellent. Okay. All right. This entry here is the 1, 2. So it'll be first row here, second column here. 4, 0, 3. Is? Second? 7. Perfect. Okay. You want to do the rest of them? So I won't have to stand and sit. Okay. Two adds to B. Perfect. Next. 2, 1. Okay, that'll be right? That'll be a -5. It will be a -3. Excellent. Next. Six. Got it. Next. Six. All right. Let's see how the book did. -5, 7, -1, -3, 6, 6. Hey, they got it right. Okay. How about the B? Here we have a 3, 4, -2, 5. Multiplied by a 1, 0, 0, 1. Okay, first, can you multiply them? What size? 2 by 2 by 2 by 2, and that'll give us a 2 by 2. Okay, so you'll have those 4 entries. Okay, that first one would be, right, 3. Next. 4. Next. -2. Next. 5. Anything you notice there? Same as what you're multiplying. So it appears to me, oh, is that what identity was saying? That's the identity matrix. And that's exactly like the identity element in multiplication. Multiply 17/3 by 1, and you get 17/3. So you multiply any matrix of the appropriate size by the identity matrix you can multiply by that. That has to be squared, by the way. And it has to be whatever the number of columns of this, that has to be the square of that. You multiply with that, you're going to get identically the same thing. That's the identity matrix. That's why they call it that. One reason, anyway. Okay? C. See if we can fit this in. 1, 2, 1, 1. Multiplied by -1, 2, 1, -1. Can you multiply those two? What size will it be? Okay, let's do it. One, you got it. Second. Okay, let me show me how you got that.
1 times 2.
All right. That's a 0. Okay. Zero and really? One. Oh, what did you get there? You got the identity matrix. So I'm guessing that these two must have some special relationship to give you that. Now in real multiplication, real number multiplication, what two numbers would give you the identity element when you multiply them together? 1 and 1 certainly does. Is that the only one? can you multiply by 5 to get 1? 5 by 5 doesn't give 1/5, exactly. Or negative 12 by negative 1/12. That'll give you 1. Well, there is a sense, and those are called multiplicative inverses of each other, right? The reciprocals. Later we'll find out that these are inverse matrices of each other. This is the one and only time that if you reverse the order here, you can use them, you'll still get that. Okay? So those are the special matrices that are commutative, the ones that give you the identity matrix, and they are what we'll later call inverse matrices of each other. Okay. Now we could almost fit in D, but why crush it? Let's just go and erase and do D. And this is a 1, negative 2, 3. I think it's a negative 3. Multiplied by a 2, negative 1, 1. Wait a minute. What in the world are those? There are 2 different names you can give to this. You could call that just a row matrix by a column matrix. Or the other name is a row vector by a column vector. Anytime it only has one dimension, you can call that a vector. Now, what are their sizes? 1 by 3, and this is a 3 by 1. Can you multiply those? And what do you get? Okay. That's all you get. Okay? Do it to it. 4, 1. Okay. Now, that happens by chance to be an identity matrix itself. It just only has one entry, and it's 1. But we don't talk about 2 matrices being inverses of each other if they're not square. So that's the other thing. They have to be square matrices, even though that does produce an identity matrix. Okay? And then E is 2, negative 1, 1 multiplied by 1, negative 2, negative 3, which I think is the same 2 matrices, right? Just commuted. What size is this one? 3 by 1, and this is a 1 by 3. Can you multiply those? What do you get? A 3 by 3. Okay. So we've got 9 entries to compute. So let's start. 2, negative 4, negative 6, negative 1, 2, 3, 1, negative 2, negative 3. Okay. So, as I said before, we don't call, even though that did produce technically an identity matrix, you don't consider those inverses of each other because they're not square. Okay? And obviously when you reverse the order of those 2, you get something very, very, very different from an identity matrix. In fact, the same identity matrix, no way, they're not even the same size. Okay? And nowhere close to being identity matrices. Let's see if we got them right in the book. 2, negative 4, negative 6, negative 1, 2, 3, 1, negative 2, negative 3. Perfect. All right. Now, remember, one of the, not the only, but one of the reasons we do matrices is to solve systems of linear equations. So let's see what happens, if anything, when we have one practical application of matrix multiplication is representing a system of linear equations. Here, note here is a system. A11x1 plus A12 x sub 2 plus A13 x sub 3 is equal to B1. A21 x sub 1 plus A22 x sub 2 plus A23 x sub 3 is equal to B2. That's a 2. It's an ugly 2. Okay. And A31 x sub 1 plus A32 x sub 2 plus A33 x sub 3 is equal to B3. All right. Now, you can rewrite that system of equations as matrix A, which is just what you would expect, A11, A12, you know, blah, blah, times vector X, okay, well, okay, sorry, I'm jumping the gun here. They do it this way. This matrix A, A11, A12, A13, A21, A22, A23 times A31, A32, A33 times a vector x sub 1, x sub 2, x sub 3, and you get a result b sub 1, b sub 2, b sub 3. Okay. They say you can rewrite that way. Let's see if indeed that's true. First, can you even multiply these two together? This is a 3 by 3. That's a 3 by 1. What's the product? 3 by 1. Okay, so at least the sizes make sense. 3 by 3 times a 3 by 1. Wipe out the 3's and you get a 3 by 1. Okay, the sizes make sense. Let's see if the values make sense. Right? A11x1 plus A12x2 plus A13x3 is equal to B1. Hey, that's exactly that equation. This one is A21 plus A22. A21x1 plus A22x2 plus A23x3 is equal to B2. That's exactly that equation. And A31x1 plus A32x2 plus A33x3 is equal to B3. That's exactly that one. So this is a correct representation of that system of equations. Okay? But this is written in matrix multiplication terms, which you can say A, that's a typical matrix for A, times vector X, column vector X, is equal to column vector B. Okay? Now, you don't have to bold, but most of the time they do because those are column vectors. Okay. Now, kind of keep up with time for me because I've got a student coming in between this class and the next class. I only have 30 minutes to eat lunch. She's coming in those 30 minutes, so I don't have much spare time, so don't let me run too much over. So solve the matrix equation AX equal 0, where 0 is the appropriately sized 0 vector, okay? Where A is 1, negative 2, 1, 2, 3, negative 2. x is x1, 2, and 3. Okay, and of course the 0 vector. You tell me what size it needs to be. This is a that's a 2 by 3. This is a 3 by 1. So sure enough, that needs to be a 2 by 1. So what would it be? 0, 0. All right. Vector 0 is the 0, 0 vector, the appropriately sized one. Okay. Okay. Now, what's that? Yeah, what we're going to do is remember how we solve. Okay, so this represents then, both of these represent this system of equation. x1 minus 2x2 plus x3 equals 0, and 2x1 plus 3x2 minus 2x3 equals 0, right? Multiply those out to get that. That's the matrix equation up there, okay? Now, if that's how we had started, and said, let's solve this using Gauss-Jordan elimination, what would you have done? Yeah, and what matrix would that be? Okay. Now, what's the first thing you want to be true? One, and we got it. Good for you. Okay. Next. 0 below it. How do we make that happen? Right. So let's do that to it. We're using the first row, so we write it down 1, -2, 1, 0, and do what it said. 0, 7, -4, 0. Okay? What's the next thing we want to happen? A big boo hiss, but yep, and how's the only way we can do that? By 7, yeah. I just did it, okay? So this will become a 1, -4/7, one of my favorite numbers in the world, okay? And what do we want to happen next? -2 to become a 0, okay? So we're using the bottom row, which is 0, 1, -4/7, 0. All right. What would be the top row? Oh, wait. How do we make that happen? I'm going to, if you don't mind, going on to erase this because this is getting hard to see, and put a 1 there. I can do it because I have a magic pen. Okay, so how are we going to make that negative 2 become a 0? No, 2 times row 2 plus row 1, right? One, 0, yep, and 0, right. All right, now what does this yield for us? Okay, or if you let x of 3 be a parameter, their favorite is t, this would be x of 1 equal to 1/7 t, and x of 2 is equal to 4/7 t. Okay, so your ordered triplet, which is your answer, would be t over 7, comma, 4/7 t, comma, t. I think. Okay. Now, that's one way to express it. If you don't like having the fractions, multiply everything by 7. And you would get t, 4t, 7t. And that's kind of what they get here in the and they, of course, expressed it as a column vector, t, 4t, 7t, okay, and that's one way to express it. Then they pulled out the t and said t times 147, and there's a variety of solutions. 147 is certainly one. Then double that and you get 2, 8, 14. 0, 0, 0 certainly would work, and -1, -4, 7. Any multiple of that will work as a solution. So there's an infinite number of those solutions. Okay. Now they do have a little technology blurb there. If you do have a package such as this, you can certainly use it. Okay. How are we doing on time? 18 minutes. Oh, that's good. All right, let's clear this and go to partitioned matrices. I'm trying to think why they're throwing this in now. I can't really think of any good reason. Yeah, I think I know. So here's starting with the same type thing we did before, AX equal to B. Okay? It says this can be represented in a more convenient way by partitioning the matrices A and X in the manner that just in the manner shown below. I thought they were going to say why they did it, but they just said shown below. Okay. So here's matrix A as we usually have it. A11, A12, A13, dot, 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 A1N. Yep, that's the one we're using. A21, A22, A23, dot, 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 A sub 2, 2N, A31, A32, A33, dot, 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 to A3N. Then we'll continue dot, dot, dot down to you get A sub M1. I hope is what, yep, that's what they use. This one dot, dot, dots down to A sub M2. This one dot, dot, dots down to A sub M. My M's and my 3's are looking too close to each other. If I'm not watching what I'm writing, they sort of go all over the place. A sub M3, and then dot, 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 to dot, 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 to dot, 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 and dot, 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 to A sub M N. Okay. Takes so long to do. Your X. Okay. Now this takes a little bit of thought here. Remember, AX has got to be B. So what's got to be the dimension of X?
So it's going to be 3 by 1.
Second?
Yeah, 3 by 1.
Not 3. We don't know. See, what's the dimension of A? Second?
N by N.
N by 1. It's just a vector. N by 1. So this is X of 1, X of 2, X of 3, dot, 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 down to X. X of N. Okay. Add what would be the dimension of B. As you said, this is an M rows by N columns. That means this has to be an N rows, and you know it's got to be a 1. Okay, so this is an M by 1. So the B is B1, B2, B3, dot, 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 down to B sub M. Okay, so they sort of look like they're the same, but they're not. Okay. Now, they just left it as B, which is fine. I don't know why, but they did. Okay. Now, if you were to multiply these two, this is sort of going backwards, but that's exactly what we did. A11 x sub 1 plus A12 x sub 2 plus A13 x sub 3 plus dot, dot, dot times A goodness gracious, my head just went nuts on me. Started hurting like crazy. A sub 1n x sub n, okay, is equal to B1. except they don't do the B1s. I probably shouldn't either, so let's just leave this. We're just going to do this system of matrices, but this is just one entry, and that will be your B1. So I like putting it there. Next entry would be A21 x sub 2 plus A22 x sub, no, this is x sub 1, x sub 2 plus A23 x sub 3 plus dot 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 A sub 2 n x sub n is equal to B2. A sub 3 1 x sub 1 plus A sub 3 2 x sub 2 plus A sub 3 3 x sub 3 plus dot 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 plus A sub 3 and yuck. At some point the writing just falls apart. Okay. X sub n, that's going to be your B3. Okay, we'll dot 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 this down to A sub m1 x sub 1 plus A sub m2 x sub 2 plus A sub m3 x sub 3 plus dot dot dot, everything's a dot dot dot. Yeah, everything's a dot dot dot. Goodness gracious. Plus A sub m n x sub n, and that's your B sub m. M isn't writing, there it goes. Okay. Now, this is kind of where they say, or you can do this, okay? Now, what they're noting here is that the first terms here all are multiplied by x sub 1. So they say partition this and make this a column vector and m by 1 and multiply that by x of 1, okay? And you're going to get an m by 1 well, let's just use that representation there now. Yeah. I like to put the a's first and the x second, but they do it the other way. So what doesn't really matter, I'm going to do it my way. Okay, a sub 1 1, a sub 1 2, 2 1, a sub 3 1, dot dot dot, a sub m 1. This is times your x sub 1. Okay, plus second columns there are a sub 1 2, a sub 2 2, a sub 3 2, dot 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 down to a sub m2. This will all be by x sub 2. Okay, plus, I'm going to run out of room. Maybe it's fortunate. Okay, a sub 1 3, a sub 2 3, a sub 3 3, dot 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 to a sub m 3, and that's going to be by your x sub 3 plus, and then you'll just go on down the list and do it. This is x sub 3. I said 3 and wrote 2. Okay, and you keep doing this, and basically what you wind up with is a partitioned matrix. You got a column matrix of your column here times your x of 1, column matrix of the second column times the second component of your x, and then third all the way up to your nth component. And that's equal to your b vector. Okay? Now, what you call this is a linear combination of your column matrices. And your column matrices are the linear combination of column matrices, and they rewrite these to be A sub 1 because that's now a column matrix. This will be A sub 2, that's a column matrix. A sub 3, that's a column matrix, or a column vector, and that's why I'm writing them as vectors. And the coefficients of them, which kind of turns everything on its head, because these are your coefficient matrices, right? And that was your variables. Well, now, when you do it this way, this is a column matrix, and that's the coefficient of this column matrix. Now, it's not really a numerical coefficient, it's a literal coefficient, but it is indeed what they do. So it's, kind of turns things around, okay? Now, I think, and again, I'm not really sure why they're doing this here, except you can. It's a perfectly legitimate thing to do. But here's a summary that they have. How's our time?
5 minutes.
5 minutes, okay, so I can get this one done. The matrix product that we just had, AX, which we're going to say is equal to B, but we're not going to say that yet, is a linear combination of the column vectors A1, A2, up to A sub n that form the coefficient matrix A, and we have that x sub 1 times A1. Now, x sub 1 is a component of your variable column vector, okay? But they've turned it around to make it a coefficient of another column vector, okay? Plus x sub 2, A sub 2, I'm shortening it, x sub 3, A sub 3, plus dot, 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 all the way up to and including x sub n, I think it is, yeah, times A sub n. Now, remembering this A sub n is A sub 1 n, A sub 2 n, A sub 3 n, dot, 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 down to A sub m n. Okay. That's what that stands for, and that's why it's called A sub n, because there's n elements in it. Or it's the nth column. And that system is consistent if and only if B can be expressed in such a linear combination of your x sub 1s and your column vectors. Okay. Now, let's clear that. Do we have time for example 7?
2 minutes.
2 minutes. I kind of doubt it. Okay, so we'll begin with example 7 next time. Okay? And, that was the last example. And as I said, I didn't think they were going to do much with it. But homework exercises would be 1 or 3, and you can find capchat.com for the worked out solutions. Any of the odds 5 through 9, they're all at CalcChat. 11 or 13, they should be at CalcChat. Any of the odds 15 to 27, they should be at CalcChat. 29 to 35, they should be at CalcChat. Okay, try 37. I think you can do that. And start trying to work on 39 through 47. Okay? I think you can do those. We'll pick up the rest of those next time. All right, good deal. Have a good weekend. Yeah, we'll see you Monday.